Yeah. Perfect. He's on his own. He's by himself.
Hi everyone, my name is Joshua Geronimo.
I'm Jonathan Gollum.
And I'm Sonia Serrano.
And we're in the Department of Electrical Engineering with our professor Ethan Wayne and our DLS, Mark Xu. And our project that we worked on for the past 8 weeks is the design and implementation of quasi-Yagi antenna for 4G communication.
So the current generation of mobile data technology is 4G, and 4G was a massive improvement upon 3G, and it improves many users' experience in connecting to the internet, so it really helped to improve the connectivity of the world. The problem we have though, however, is that as advances are made in mobile data technology, the base stations which relay the data signal are having to become closer and closer. And we want to solve this problem by creating a high-performance antenna so that the range of these base stations increases and we don't have to have them every 200 meters or so.
So first of all, what are antennas? Most antennas are the device that receives and transmits information in the form of electromagnetic waves. And what this means is that they are reciprocal devices, which one device can do this same job at the same time by receiving and transmitting information. So, as you can see in this diagram represents a quasi-Yagi antenna, which was the one that we designed. But it can, right now I'll explain the process about how all types of antennas work. So first of all, they receive the information in the form of a guided wave through the transmission line, which is also known as a cable, and then it's fed into the antenna through the microstrip feed right here. And then from there it goes to the coplanar plane here, which it's then radiated into the free space throughout the driver. So all antennas radiate in all sorts of directions, but in our case, we want to just focus it into one single direction so that we can have the most powerful transmission. And the thing is, in our antenna, the director, as seen here, and the ground plane, which is the gray, which is on the back, that controls the direction in which the information is radiated to. And then all these main components into which the information is fed into is made of copper, and the copper is on the substrate, which basically just improves the antenna performance.
So for our motivation in creating the quasi-Yagi antenna is that it's lightweight, it's pretty cheap to make, and it's compatible with all kinds of frequencies on a certain bandwidth. So the reason why it's good for it to be simple is that we could make it quickly and easily so that you can make it in an array, because some antennas work as if you stack one on top of another, so they all radiate in one direction. And the reason we use this kind of antenna is because it has a larger bandwidth being the range of frequency it could use, less mutual coupling. That means that it won't get interfered with any other antennas near it. A high radiation efficiency because all the radiation radiates in one direction. Low crosstalk between elements is because our antenna is a 1.9 gigahertz antenna, so that not many devices use it. They usually use a 2.4 gigahertz because the 1.9 is only used for cellular phones, and then that it has a broadband 4G connection and it's uniplanar in common.
So right now I'll be passing out the prototypes that we made of our antenna so you guys can actually see it.
So the process for antenna design is somewhat as follows. We start with a 3D model that we create in a software named HFSS, that stands for High Frequency Structural Simulator. And using this software, we can then run a simulation to predict the behavior of the antenna without actually having to build it. We still have to build it after that though, because we can't fully predict how the antenna will behave and perform in the real world. Once we get both the simulation results and the actual testing results, we can either say that, okay, this meets our expectations, or if it doesn't, we have to go back and modify the dimensions until we get the ideal antenna.
So first, as he explained, we have to fabricate the antenna. the first step is that we have to create a mask, which is a clear plastic which has the outline and dimensions of our antenna in red. And then from there, we use this outline to do the etching. What this means is that we get the material, which was a substrate and copper on both sides of the substrate, and using chemicals, we get the outline of the antenna onto this material, and then we dip it in iron chloride, which then gets rid of the excess copper. And so on one side, we're left with the design of the antenna with like these features like the director and the driver and the feed. And on the other side, we have the copper ground plane. After this, we have to test the antenna. And one way we do this is that we use the radiation pattern. And this is measured in a anechoic chamber. And so in this process, we get we can map out the power and the direction of the transmission. And then we also have to test it using the network analyzer, which measures at different frequencies the front to back ratio, which basically compares what is transmitted in the direction that we want it, and it compares it to the rest of the information that's being transmitted in the direction we don't want.
Okay, so what she was explaining back there in the testing part is a network analyzer, and it'll show the reflection rate, which is the S11, of what frequency we're trying to find. So in our simulation, when we ran it in HFSS, our simulation was around 1.9 gigahertz, almost touching the 1.8 and 2.0. Well, we were fine with that because that's the bandwidth we need. But when we did it in real time, real life, the antenna actually radiated pretty well on the 1.9 right here. It just had a little frequency shift to the right towards the 1.8, but that was fine because the S11's reflection rate was pretty good.
The other part of the results that we got is the radiation pattern. And on the left, you can see the 3D radiation pattern. And from this bubble-looking thing, you can deduce that the antenna radiates strongly, or more strongly in one direction. And on the right, you see a cross-section of that same 3D radiation pattern, but it's cut across the XY plane. And once again, you can see that it is radiating strongly in the direction that we want.
So in the future, we want to improve like 4G network communication systems by improving the basic component of it, which is an antenna. In our case, the Quasi-Yagi antenna. And we want to improve it so that we can get to 5G. And this will improve the internet speed, and it will make it more reliable, and we will be able to have more devices connected to the internet without sacrificing the quality that they receive. Thank you.